So unless you get extremely lucky, the majority of times whenever you're trying to name an alkane, you're going to get a relatively complex structure. And this structure is probably going to have a whole bunch of branching off of the main structure. You may get even more unlucky and you might have, some other oxygen substituents, nitrogen substituents. For now, we're just going to focus on what if you only had carbon. And even if you just have carbon, the naming can get a little confusing because you can have all of this random branching that comes off of these carbon structures. So if you're trying to name relatively simple but still somewhat a little complex alkanes, there's a generalized way to name these, and it consists of 3 parts. And these parts are going to be the prefix, the parent, and the suffix part of the molecule. And now before, I know that in the previous video we were talking about prefixes, and we said that these would be the meth, eth, prop, but, but that turns out this is only really if you have extremely simple structures. But whenever you get a little bit more complex and you have this kind of branching, what the prefix is really meaning for this kind of equation is that the prefix is telling you what are the substituents that are branching off, and where are they actually located. The parent is actually what the prefix would be in the previous video. So we would be talking about meth, eth, prop, but. And this is really telling you about what is the longest part of the chain. So again, the parent is telling you the longest carbon chain that you can potentially count without interruption. And the prefix is telling you about what and where are the substituents. When I say substituents, really what I'm talking about are what are the branching units. So now we have a definition for what a prefix would be, we have a definition for what the parent would be, and so now to talk about the suffix is really the main functional group. And in the previous video we talked about priority, and we said that alkenes have a higher priority than alkanes, and so it would be the same with alkynes. Alkynes would have a priority over alkenes. So if you had an alkyne in the molecule and you had an alkane, the suffix would really kind of default to the alkyne suffix, so the -ine instead of the -ane. So the suffix is again the main functional group, and they'll just abbreviate functional as FXN. So now let's take a second and go back to the prefix and examine what we really mean by substituents. And really when we say substituents, all we're really trying to say is there's a way to describe a certain number of carbons that are attached to the main unit. So these are kind of like offshoot units. So let's just take this very simple example of meth, eth, prop. So this would be a propane, and so this would be a propane molecule. So what we could do is let's just pretend for a moment that we've decided that this propane, how would we call it if it was a branch off of a main parent chain? The way we would do that is we would pretend that this carbon was bound to a main group. And so instead of having 3 hydrogens here, we would really just have 2 hydrogens. And these would be bound to something else. So this little squiggly line is just my way of saying this group is bound to something else. We're not sure what it is, but it's just kind of something, we're kind of ignoring it. And so what we do is this would normally be a propane molecule, meth, eth, prop. But as soon as we say, okay, this is now a branch, this is a substituent, this becomes not a propane anymore, this becomes a propyl group. So this is a propyl group, and basically what we've done is we've removed the -ane and we've just replaced it with a YL as the suffix. Another common way of drawing the propyl is if instead maybe we have meth, eth, prop, and instead of having that branch starting here, if we had the propyl kind of attached to a different main chain over this way. So now what we've done is we've just replaced the 2 hydrogens here with a 1 hydrogen here, and what we're saying is we still have meth, eth, prop, but this middle part of the prop is actually attached to what we would refer to as the main chain. If this is the case, then instead of calling it meth, eth, propane, we can't really call it a propyl group because this is the propyl group. And so this kind of configuration actually has its own kind of common name. And so what we say is this is called an isopropyl group. And so what we've done is we've still replaced the ane with a YL, and what we've done is we've added this iso to kind of indicate where this propane group is attached to the main parent. Another example would be, what if we had a butane? So if we had a butane, meth, eth, prop, bute, if instead of having a butane, what if we had this butane attached to a main branch unit? In that case, we would just say, okay, meth, eth, prop, bute, this thing is attached to something else, not sure what it is quite yet. We can keep track of the hydrogens here and here. So we have 2 hydrogens here. And so just like we took propane and made this a propyl, once we said this was a branch, we can now say this is a meth, eth, prop, butyl, so a butyl. So this would be a butyl branch. And the butyl actually has its own common forms as well. So instead of calling this a butyl, what if instead we had a slightly different configuration? We still have 1, 2, 3, 4 carbons, but we had it attached to a molecule in a slightly different way. So this is another isomer of butane, 1, 2, 3, 4, so meth, eth, prop, bute. But what we've done is we've slightly changed the way that the carbons are attached to each other, and so this looks kind of like a little crow's foot. And we still have this meth, eth, prop, bute attached to a main, parent group, but it's attached in a slightly different way. So just like the propyl had this kind of funky common name to kind of describe where it's attached, so does this group right here. So this group is so common it gets its own name. This is called a tert butyl. So again, the eel kind of says that it's a substituent coming off of a main chain, and this tert part is trying to tell the audience that we have this kind of chicken foot orientation. So these are 2 common substituents that you'll see over and over again. So if I ever say isopropyl or if I say tert-butyl, you'll know what I'm talking about. And so same thing is if we have a propyl or a butyl, you'll understand that the YL indicates that this is some kind of substituent or some kind of branch coming off of the main group. Okay, so once we are kind of happy with talking about prefixes, it really actually makes a lot more sense whenever we talk about naming a parent part of the molecule. And so the way that we define the parent molecule is we say that the parent part of the molecule is the longest, we should really say unbroken carbon chain. So the longest unbroken carbon chain that we can find. And it might seem like a trivial task to find the longest carbon chains, but sometimes it's actually somewhat difficult. So here's a carbon molecule, a carbon-based molecule, just carbon. So pause the video and try to find what you think is the longest carbon chain. So some people might have found this kind of red configuration here, and in this case we have 1, 2, 3, 4, 5, 6, 7. So this seems like a pretty promising lead. That's a lot of carbons, but it turns out that that's actually not the longest unbroken carbon chain. It turns out that the longest unbroken carbon chain is right here in green. So this is 1, 2, 3, 4, 5, 6, 7, 8. So here what we do is once we find the longest carbon chain, which is actually just an unfortunate kind of trial and error process, what you do then is you can call the parent by the number that is indicated by the longest chain. So in this case, since we had 8, before we had to count to 10, this would be a parent name of oct, O-C-T. So this would be an oct parent name, okay? So it turns out that oct would be the parent, and the suffix is an ane, because the ane is just, the main functional group, and this is going to be all sp3 hybridized, so everything is an ane. So what we do now is once we find the parent and once we figure out the suffix, we can kind of go back and sweep up anything that's left over. And that would include these 2 groups right here. And at this point, it probably makes a little bit more sense when we were talking about substituents and branching whenever you look at this molecule. Because if you look here, this methyl isn't really part of the main unit, and this ethyl really isn't part of the main unit either. So what we have to take care of is this substituent, so this methyl, and we have to take care of this substituent, this ethyl. So if you think back to the purpose of the prefix, we had to say what was a substituent, what was a branch, and also where are those branches? So where are the substituents located? And this is actually a little bit more of an in-depth painful process than you might imagine, because it turns out that not everybody sees a molecule in the exact same way. So we had to come up with rules to figure out how we can communicate effectively. So what we could do to talk about where is we can just number the carbons in the parent. So we could number from the left, and in that case this would be 1, this would be 2, 3, 4, 5, and 6, 7, 8. So that would be if we were in this party that liked purple, and we could number from the left. But what if you were in a different group of people and you didn't see the molecule this way? What if you started numbering from the right? And in that case, this would be 1, 2, 3, 4, not 5. So now we're in this yellow party, and this would be 5, 6, 7. So the question is, whenever we're talking about where the parent is the substituent, we have two different numbering schemes here. So it's only descriptive if we can agree on how we number the where. And so the way that these arbitrary rules were set up is that the way you number is that you want to minimize this number that you get for the initial substituent. So if we numbered from the left, the initial substituent would be the methyl, so 2. And if we numbered from the right, the initial substituent that we would hit would be this ethyl, so that would be 4. So if we had to choose between a purple 2 and a yellow 4, the color doesn't matter, I just randomly chose it, 2 is the smaller number. So in this case, the party or the group that we go with is this purple group, because the purple group gave us the smaller number from the first hit on the substituent. So purple actually wins out in this case over yellow. So the way that we would number the where, or describe the where, is 2 and 5. And so the way that we would write this down then would be, we would say 2-methyl is the where and the what, and then we have a 5-ethyl. So 5 and ethyl. And I don't know why I'm using yellow instead of purple. Purple would have made more sense. Whatever, just kind of go with it. So 2-methyl, 5-ethyl, both the where and the what. We have to somehow combine this with the overall parent, which is oct, and the suffix, which is ane. So it turns out there's one little nitty-gritty rule that you have to kind of go with to be able to go with convention, and that is, what order do you put these things in? Do you put the 2-methyl first, or you put the 5-ethyl first in the name? And it turns out the way you break this tie is by alphabetical order. So the way you would name this is you would compare the M versus E and any other substituent, and you would order them in the final naming by alphabetical order. So in that case, 5-ethyl goes first. So we would name this molecule 5-ethyl 2-methyl octane. So the final name for this molecule is 5-ethyl 2-methyl octane. So don't get suckered into ordering the substituents by number. That's not the way we order. We order it by the alphabetical priority of the substituent itself.